Hello, good day, respected faculty members. Today, I am the Salman Al Mamun and fellow teammates Mahfuz Rahman, Jarif Ahmed, and Tasbih Tabassum. Representing about the project, we decided to work on for the course EEE 435, a gesture-controlled robotic arm. We chose this project after much discussion and cost analysis to ensure it doesn't exceed the budget limit of our teammates, as well as the fact that we found the concept fascinating. Here is a timeline on what each of my teammates will present. Tasbih Tabassum will be presenting project objective. Jarif Ahmed will be covering word theories and concepted gesture-controlled robotic arms. Functionality is based on, and Mahfuz Rahman will be summarizing the topics covered and give a small background on current industrial applications of gesture-controlled robotic arms or robotic arms in general. Now, Tasbih Tabassum will present the objectives parts. Thank you.
This is Tashfia Tabassum. Today I will be presenting the objectives of our project, which is the hand gesture control robot. The goal of this project includes utilizing enhanced intelligent methods for hand gesture recognition. Our goal is to produce a 3 degree of freedom robot with minimalistic and simple design. As we can see in this relationship tree, the 3 degree of freedom robotic arm will provide us high performance, high speed and accuracy, will be easy to operate, it will be durable, portable and very affordable, it will be lightweight, small in size and sustainable. Even though there already has been plenty of research in gesture recognition by a robotic hand, more research is required to make the gesture recognition process more accurate. We are going to perform kinematic measurements to understand how the hand functions based on its kinematic properties. We are going to study different grasp styles, joint types, etc. Hopefully, the study of the kinematics of the robotic arm is going to lead us to the invention of improved humanoid robots and prosthetic hands. The robotic arm will operate in three-dimensional space, having 3 degrees of freedom. The robotic arm is built like a human arm. The model we are presenting has 3 degrees of freedom that includes the change in orientation through rotation about 3 perpendicular axes. These axes are one of them is the pitch or the transverse axis, another one is the yaw or the normal axis, another one is the roll or the longitudinal axis. The rotational envelopes are tilting side to side on the x-axis, also known as the roll, tilting forward and backward on the y-axis, also known as the pitch, tilting left and right on the z-axis, also known as the yaw. Here is the picture representation of how the rotational envelopes are placed in an object. As we can see in the picture, the stationary part of the robot to which all the other parts are attached is called the shoulder, and the links are very slender so that it could be lightweight as it is very important for reducing power consumption during its operation. The joints are revolute. The hand of the robot carries the end effector. In the next slide, we can see that for performing kinematic analysis, an XY coordinate system has been attached to each link. There are 3 links in this graph and 3 XY coordinates has been attached to these links. A1 is the length of the first link, A2 is the length of the second link, A3 is the length of the third link. Theta 1 is the angle between x0 and x1 axis. Theta 2 is the angle between x1 and x2 axis. And theta 3 is the angle between x2 and x3 axis. Thank you for listening, and my teammate Zarif will continue from here.
Thank you, Tasfia, for explaining the project goal along with relevant theories. I will now be talking about the hardware components that we require to accomplish this project. So for the implementation of this project, we will be using an Arduino Nano board as our microcontroller, an MPU 6050 sensor, which is a combination of an accelerometer and a gyroscope for our gesture control, NT996 servo motors for actuation, and last but not least, a 3D printed hand. I will briefly elaborate on what each of these components are, their architecture where possible, and how each of them functions. An Arduino Nano is one of the cheapest purchasable microcontroller boards with programming capability, which allows users to perform multiple simple IoT-based tasks. We chose this board for its budget friendliness and ease of operability. It can be easily set up and programmed through plug and play by attaching it to a computer via a USB cable, which is included with each Arduino Nano, and program it via any of multiple programming languages, including Python, Java, C++, etc. It is also compatible with multiple IDEs, including Arduino's very own IDE, uh, or most other popular programming platforms. IDE stands for Intelligent Development Environment, which is basically a programming platform. An Arduino Nano board consists of a built-in Atmega 328P microcontroller, uh, 8 analog input-output pins, 14 digital input-output pins, 1 transfer pin, and 1 receive pin. 2 of the digital pins acts as a secondary ground and reset pin, even though there already is a separate ground and reset pin on the side of the analog pins. It can either be powered by connecting it to a phone charger or computer through USB cable, or through its input pins, which can optimally handle a power source of 7 to 12 volts. The operating voltage of the board is 5 volts, and it also allows an output voltage of up to 3.3 volts through a voltage output pin to any devices or sensors connected through it. The lightweightness and small dimensions made the Arduino Nano the optimal choice of microcontroller for our project. For gesture control mechanism, we will be using an MPU 6050. It is a microelectromechanical system, which is a combination of a 3-axis accelerometer and a 3-axis gyroscope inside which inside it, which makes it more accurate in determining changes in position than it does to use 2 separate sensors that act as an accelerometer and a gyroscope individually. It is overall cheaper and helps us to measure acceleration, velocity, orientation, displacement, and many other motion related parameters of the robotic arm. The gyroscope measures rotational velocity or rate of change of angular position over time along the x, y, and z axis. It uses microelectromechanical system technology and the Coriolis effect for measuring. The outputs of the gyroscope are in degrees per second. So in order to get the angular position, we need to integrate the angular velocity. The accelerometer can measure a gravitational acceleration along the 3-axis, and the angle at which the sensor is positioned can be mathematically calculated. So with the help of the accelerometer and the gyroscope data, we can get a fairly accurate measure about the sensor orientation. Both the accelerometer and gyroscope is embedded inside a single chip, which uses I2C or Inter-Integrated Circuit Protocol for communication. It also comes with an inbuilt temperature sensor. Actuation is a very important aspect of robotics that involves motion. Motors are the bread and butter of any modern electronics that require motion or actuation, for the fact. This is especially important when it comes to robotics. In order to ensure accuracy, we needed a powerful motor that can reduce any possible margin of error. The type of motors that fit this description are servo motors. Servos consist of a DC motor connected to a control circuit and a potentiometer, which uses an error sensing negative feedback to make sure motion output match desired results. To keep our project budget friendly, and since we needed powerful servo motors, uh, MG996R servos were our optimal choice. Servo motors function as the actuators in robotics. With the components covered, our next member, Mahfouz Rahman, will be summarizing the things covered along with a few examples of industrial applications of robotic arms with similar designs. I give the floor to you, Mahfouz Rahman. Thank you.
Hello everyone, my part is application and synopsis. I will describe application part in general. We had to do a project with 3 degrees of freedom for budget limitations. We were aiming to replicate movement that the human hand is able to do and avoid movement that a human hand is unable to do. We were also trying to find out which kinematic properties of the human hand are important and should be implemented in a humanoid hand. The selection of MG996 servo motor and Arduino Nano makes our project easy to carry and small in size. The Arduino Nano microcontroller was easily programmable without using a device burner. Our robotic hand can be used in different sectors. It can be used in small stationary robot. It can be used as a small stationary robots. The geometry of the hand is complex and is hard to construct in a virtual environment. The functionality and the degree of freedom of the hand encourage researchers to develop hand like an instrument. It is a small economical manipulator to cooperate with humans. It is also feasible to use in small and middle-sized enterprises. It can also used in planting robots and it can be also used as a planting robots in agriculture company. It can be helpful to both the agriculture and food industry. It can also be used in mobile manipulator. The mobile platform extended the workspace for the arm and the arm offers several functionalities. Our 3-degree freedom robotic arm can be used in surgical robots in the medical field and for manufacturing product in the industrial field. We hope that our project will be useful in different fields where less expensive and containing less dead weight robotic arms are needed. That's all from our side. Thanks for listening.